Good afternoon. Today we will have the 8th lecture in the series on statistics in research methodology. Let us have a quick summary of the topics till date. We started with the roles of statistics in various phases, then the physical quantities and the factors affecting their measurements, namely measurements, measuring tools, personal environment of the measurement, then results of the measurements, how we can appropriately represent the results, then the factors such as accuracy and precision of measurements, significant figures, place values, rounding of digits, as well as the rules pertaining to each one of these. There are propagation rules for various operations, starting from the simplest addition, subtraction to the exponential, logarithmic, and all. Even the trigonometric functions we did see. The types of measurements, namely gross, systematic, random errors, and the sources of all these three different categories of errors, the ways to tackle each one were discussed. Characteristics of repeated measurements were ascertained through the utility of Gaussian distribution function. Later on, we went ahead with confidence interval, confidence level, and confidence limits of the measured data in order to encompass the true value within the range of the measured values. For completion of the discussion, we had seen the difference between the discrete and continuous probability distribution functions and various formulae for that one, and got practice on each one of these. In the last class, we had learned about the hypothesis testing via the Z and T statistics, the context where one has to apply which particular statistics. And later on, we went ahead to understand the two different types of errors during hypothesis testing, which are called type 1 and type 2 errors, otherwise alpha and beta errors, and the flow diagram for doing the stepwise procedure of hypothesis testing. And in the last class, there was one small set of this exercise for you to do yourself was given, wherein the T table was given in order to find the values of T pertaining to certain confidence level, which in turn is nothing but 100 minus the significance level, and the degrees of freedom, that is one number less than the total number of measurements. The data given on the purple font color in the right hand side table are the answers to the questions given in the last class, that is lecture 7. Once you know the T value, the T distribution values from the table for a certain number of degrees of freedom and the significance level, you can further go ahead with calculating the confidence interval for the mu0 value, that is the true value. So that way we can define the range of particular horizontal axis value within which the true value will be lying. As far as we know the T value, the standard deviation, number of measurements, repeated measurements, and the mean value. X bar is the mean value. T is the statistic. S is the standard deviation. N is the total number of measurements. Here you have to keep in mind that while reading the T table, we have to look for the degrees of freedom rather than N. During the discussion in the previous class, we had seen that as we increase the number of measurements, number of determinations, the values of T drastically get reduced. We had seen the trend in the T value and the percentage decrement also we had seen in the previous class. So as the number of repeated measurements increases, the reliability or the precision of the measurements increases. However, beyond certain number, it was seen that the improvement is only marginal. Last discussion, we had seen that above 6 such degrees of freedom, the improvement is marginal. However, this reliability limit is not only dependent on the T value, but also the level of the original value or the mean value in which it is lying. So in addition to the number of measurements, T value, the mean position, because normally anything we report, we do the relative reporting. The relative value, the value which is coming in the denominator, the normalization factor will also have a hold on the reliability of the measurements. That is what we are going to see further ahead. Previous class, we had learned that from the t-statistic and the number of repeated measurements, 6 numbers are sufficient enough to have a very good control over the confidence intervals as far as the T and S values are concerned. As the number of measurements increases, reliability or the precision increases. Beyond 6 numbers, the improvement is marginal, as we had seen in the previous lecture. So one can define the absolute error window, which is nothing but the confidence interval. When you give the plus or minus value to the delta value, uppercase Greek alphabet delta is given. So that is nothing but the confidence interval without the sign. Plus or minus value, if you add along with the mu x bar value, it will be the confidence interval. So the width of the half width of the confidence interval is the absolute error. If not mentioned, as I told you, we go for 95% confidence limit. That is nothing but 5% significance level. Then n minus 1 degrees of freedom. That is the point we look for in the T table. From the absolute error value, we can define the reliability interval, which is nothing but a normalized factor of the error value with respect to the base value or the absolute value or the mean value. So the reliability interval L is given as 100 times delta, that is absolute error, normalized to the absolute value, that X value or the measured value. So as the X values go on decreasing, the reliability interval increases. All our efforts is to minimize the reliability interval so that your true value will be lying in a narrower range compared to the origin, the measured value. So X is the, when as far as chemists are concerned, X is the concentration of the unknown being determined, and the number of replicate analysis is assessed from the magnitude of the change in L with the number of determinations. As the number of determinations increases, the L value keeps on decreasing. So the larger the gain in the L value magnitude, width of the bell-shaped curve or the Gaussian curve, the smaller the L value, the better is the precision. So one can assess the reliability improvement in reliability by assessing the decrease in the L value. L values normally are represented in percentage. So let us do an exercise to get hold of this concept. So from this exercise, we will get an idea about how many replicate analysis should be done for the determination of a particular element or analyte at a different concentration level. In the previous class, we had seen only the dependency between the number of repeated measurements and the precision of the data. Now, we add on more factor, that is the level of concentration of the analyte in the sample. So at two different levels, say 2% of the chloride and at 20% of the chloride. Obviously, 20% is higher numerical value, and the standard deviations are also accordingly given. For 2% it is 0.051. For 20% it is 0.093. But using the equations given in the previous slide, that is the absolute error and the reliability interval, we can get an idea about what is the minimum number of replicate analysis so that we will have a very good control on the reliability interval. So this will help us to decide the number of repeated measurements so that in future we can save the time, whether by increasing the number of measurements, if you are gaining substantially, yes, we will go ahead with that one. If the gain in terms of precision is not that significant, then why to waste time on that one? So this exercise will give you the idea. We have to read, unless stated explicitly, we have to read the 95% confidence level, that is 5% significance level, and But we have to see is that we are trying to increase the number of replicate analysis. So starting from 2, 3, 4, 5, 6, in the T distribution function also, we had seen that as the degrees of freedom increases, what happens the trend in the T value. Similarly, we calculate the delta, that is absolute error, and the reliability interval using the equations given in the previous slide. We can see that the delta values as well as the L values keep on decreasing as the number of determinations, which in turn reflects the number of degrees of freedom, increases. When the number of determinations are 2, the degrees of freedom will be 1. So accordingly, we have to pick out the T value from the T distribution table. These calculations are very simple, and on the rightmost column of these tables are the magnitude of improvement in the reliability interval, L value. You can easily appreciate that as we go from 2 to 3 determinations in the case of A, that is 2% fluoride, you see that the improvement in the magnitude of improvement in L is visibly high, 16.63. From 22.99, it has come down to 6.36. The width has been narrowed down drastically. But when we go from 3 to 4 to 5 to 6 number of determinations, one number less will be the degrees of freedom. You will see that the improvement in L is not that substantial. In the case of A, that is 2% chlorine. When you go for 20% chloride, you see that the improvement is again highest improvement is from 2 to 3 when we increase the number of determinations from 2 to 3. Then later on the utility improvement is decreasing. So you can see that as the number of determinations increases, the improvement in the reliability interval keep on decreasing. So there is a famous law in economics also, that law of diminishing returns, law of diminishing marginal utility. The same applies here also. When you increase the number of measurements, whatever you anticipate as a result of increase in the measurements, the anticipated result or utility or fruit of the effort is marginally only rising. So it is for us to decide whether you go for such marginal improvement by spending more time and effort on the number of repeated measurements or not. As the concentration level of the analyte is higher, you can see that you can save the time by doing 2-3 repeated measurements itself. But recently, in recent days, the concentration levels are so low that we go to ppm or ppb level, then you can see that as the absolute concentration levels are very low, since the factor is coming in the denominator for the calculation of the reliability interval, the number of determinations should be such high so that the reliability interval could be under control. So that way, when you go low in concentration, when you go to very low concentration level, the demand on the number of determinations also rises, which is explicitly given in these two examples. So it is said that in A, the case 2% chloride ion determination, the reliability interval is greatly improved by carrying out the third analysis. That means there is an improvement of 16.63 in magnitude from 22.9 to 6.36 when you increase the number of determination. Whereas in the case of B, that is 20% chloride determination, the improvement is marginal as the interval is already narrow. The interval is narrow due to the presence of X in the denominator of L. So that is why when you do a classical analysis of any analyte, you will see that 2 to 3 repeated measurements suffice the purpose. But when you do the determination of an element or analyte in the trace or ultra trace level, one has to do repeated measurements to ascertain the presence or absence as well as to improve the precision. As we have seen the magnitude of the values via t-test, now we will go for the property of the distribution. or the frequencies of occurrences of data. When we do a repeated measurements, we have already discussed that it is not a singular line or singular linear output we get. We get a distribution of data which represents normally, in the case of natural variable, we get a Gaussian curve or random distribution curve. One can compare the distribution of a particular observation or experimental outcome with one predicted by a theory or maybe some reference model or some expert analyst or some alternate procedures. So this way we can compare graphically also whether two performers are doing well or not. For that, we can graphically see that the property of the distribution or the frequency distributions are overlapping or not. Generally, it is very easily done via the chi-square test. This is normally done to determine whether there is a statistically significant difference between the expected frequencies and the observed frequencies. These expected frequencies can be replaced with a theoretical or model or a reference frequency also. Expected frequency is a general term which encompasses theoretical model or a reference or an alternate procedural frequency. And the observed one is the one which we do ourselves. And the chi-square parameter statistic is given by the equation given over here, where O represents the observed value, E represents the expected value, and K is the number of categories. And here what we do is we categorize the observations under different classes so that the frequency distribution can be shown in the form of a curve. So the range of the horizontal axis of the curve we define in certain classes. And K is alternatively given the name degrees of freedom. Degrees of freedom is well understood by all of us right now. And this chi-square test is applied in various cases. For example, one can do the goodness of fit between two different data sets for their distribution, or whether the two different sets have comparable distribution or they have different properties. If they have different properties, they are independent. And sometimes the homogeneity or uniformity of the distribution can also be visualized via the chi-square test. However, there are some limitations which we'll discuss towards the end of this discussion. Then all these three different types of tests can be carried out using the same formula given here. And in the previous classes also, we had seen that through all the statistical tests, we do propose a null hypothesis, verify the equivalence of two data sets or two distributions or two statistical parameters. Then we derive conclusions if at all the observed value, the calculated values are less than the critical values of the particular statistic. Here also the same thing. We do initially propose the null hypothesis as there is no difference between the expected and the observed frequencies. Here the property being compared is the frequency of distribution of two data sets. One is the expected one, another is the measured one or the observed one. If the two distributions are exactly identical, then you will see that the chi-square value is 0. Which is almost an ideal situation. In real situations, you will see that there are slight deviations from this ideal behavior. Definitely, values will have some numerical chi-square values will be there. Then what we do is, as we had seen in the case of T and Z table, here also critical values of chi-square are compiled and available in the literature for the specified degrees of freedom. Degrees of freedom again have the same connotation, one number less than the total number of measurements. If the calculated chi-square value comes out to be less than the critical one, then we accept the null hypothesis. Otherwise, we reject it and we go ahead with the alternative hypothesis. Okay. The critical values depend on the significance level as well as the number of degrees of freedom, which is similar to the properties of the other distributions also. Only in the case of Z table, we had seen that degrees of freedom do not hold because there the number of measurements are infinite. In the case of T, both are having control. Both the degrees of freedom and the significance level will have hold on the values of the T. When should we apply the chi-square test? Earlier we had seen the comparison between Z and T table, when to do which test. Here, chi-square test is applied when the observations are normally run. This is also a statistic for applying to random variables. So the presumption is that the data are collected on a random basis. What will happen if we do not do a random analysis? Then there will be the personnel involved will have an intuition to choose some specific values, or sometimes a measuring device may have some memory effect. In order to avoid those problems or effects, the suggestion is go for a random accumulation of data from different parts of the population. And the data collected are supposed to be independent. That means one factor is not affecting the other one. This rule was applicable in the case of error propagation rules also. Otherwise, one has to consider the covariance of both the whatever factors are available. So these are the presumptions based on which chi-square tests are applied. And generally, when we apply the chi-square test, presumption is that the number of frequencies or the data points are larger than 50, and each class or each interval in the horizontal axis have minimum 10 data points. If in certain cases you find to have only 5 or less number of data, what we do, we club together adjoining groups and make the frequency larger than 10 so that the presumptions become valid for the specific case. The overall number of items or the data points or the data set should be reasonably large so that the distribution has symmetry, reliable symmetry, and if it is more than 50, the value will be much more reliable. And the relationship, between these functions normally should be linear. If it is non-linear or a polymer of higher order magnitude, then the contingency table is the relational table between two or more different data sets. Generally, if we have two data sets, what we do is one data set we arrange in the ascending order of rows, and the other data set, the alternate data set being compared, that we arrange in different columns, ascending columns. So that way we make matrices of the data set, one in the horizontal way, other one in the vertical way. Horizontal ones are rows, vertical ones are the columns. So that way we make the data sets which are being compared. That way, if we have two data points or on each set of such two sets, then we'll have a 2 by 2 matrix or 2 by 2 column, 2 by 2 cells column table for comparison. And the presumption is that they have linear functional relationship. Non-linear function, then the equations become a bit more involved equations you have to use. As I told you, if the degrees of freedom are more or large, more than say 30, then the reliability also increases drastically. Because as we have seen the T as well as Gaussian distribution function, as the number of data points increases, they all tend towards the normal error curve, normal probability distribution curve, the Z probability distribution curve. Similar is the case for any statistic. When the data points increases, it becomes a more appropriate representation of the entire population. The chi-square distribution also, you can see that the mean will be nothing but square root of 2 times degrees of freedom minus 1. And as the number of data points are more than 30, the standard deviation also will have a magnitude of the order of 1. Then what happens? The Z value, you know, it is nothing but x minus mu by sigma. You can see standard deviation is 1. So x, if the function is root 2 chi-square, the mean value is root 2 degrees of freedom minus 1. You can see it, the Z probability distribution will have the normal functional relationship and normal distribution, then whatever presumptions we had taken for the normal distribution curve, those all can be applied for this particular statistic also. So essentially, the statistical theory applies to the population. What we do is we extrapolate it whenever we do have limited number of repeated measurements, we do extrapolation. So this extrapolation also sometimes contributes to error factors. So be careful wherever possible. Let us do more than 30 repeated measurements. If environmentalists or demographics or social sciences people, they will have large number of data. They don't have this issue. So chi-square tests are generally by and large used by those people who handle large number of data. Contingency tables are constructed. Then what we do is we expect some particular frequency of occurrence of the data from previous experience or the theoretical prediction, theoretical modeling. Then we measure the data outcome. What we do stepwise is we will have an expected frequency. Then we can have measured values, measured frequency. The difference between these two are taken, observed minus expected, take square and divide by the expected frequency, then take the sum of the entire data set. This way we do calculate the chi-square statistic. Once the chi-square statistic is calculated, compare it with the data available in the literature for the corresponding significance level as well as the degrees of freedom. Then once the calculated chi-square is less than the critical chi-square, the null hypothesis holds. Otherwise, alternative hypothesis become valid. This is the general trend as we had seen in the hypothesis testing. We propose a hypothesis, then do construct the particular distribution, decide the particular distribution and significance level, calculate the statistic, compare it with the literature or the critical table, and take the conclusion or inference based on that. Okay. Generally, chi-square value is often used to judge the significance of variance in the population. That variance is nothing but the square of the standard deviation. What we do is take the ratio of the sample variance to the population variance and multiply it with the number of degrees of freedom. I repeat the process. You calculate the sample variance. Sample variance can be easily calculated. Then the population variance, whether it is available in the literature or you rely upon the previous experimental data from large number of measurements. Then multiply this factor with the number of degrees of freedom, that is nothing but n minus 1, where n is the total number of measurements. So this is another way of representing the chi-square function. Here again, we compare the variances, sample variance with the population variance, or else the observed variance with the expected variance. So the plot of chi-square distribution with the degrees of freedom, we had seen the table of T distribution also with the degrees of freedom. You can see that the plot is not very symmetrical and it has got only positive values. The chi-square distribution has got only positive values because you see the larger standard deviation or the larger variance is taken on the higher side, and you will have always, since it is a square term, always it will have positive values on it. What we have to know is the degrees of freedom and the level of significance level. And when you go towards a smaller number of measurements with a smaller number of degrees of freedom, you see that the curve symmetry goes off. Then it becomes a skewed distribution. So that is why initially itself we told that larger the number of repeated measurements, better will be the quality of the data being analyzed. And the chi-square function mathematically can be calculated as shown in the equation here. By comparing the calculated value with the table of chi-square for n-1 degrees of freedom at a given level of significance, if the calculated value comes out to be less, then we accept the null hypothesis. Otherwise, reject it. That is the general case we do. This one example, all of you can give a try. The answers are also given here in order to appreciate the use of chi-square function to decide upon such context. Like for example, somebody is measuring weight of 10 students and the list of weights of each one is given here in the table. Can we say that the variance of the distribution of their weights of these 10 students is approximately 20 kg? If you see, the weights are in the range of from 38 to 53. Whether we can say that the distribution, the variance is around 20 kg. How can we decide upon? That can be done via this chi-square testing as discussed in the previous slide, the equation. We can see at different significance level whether this data agree with the null hypothesis or not. What we have to do is calculate the sigma s square sample variance, and the population variance is given here as 20 kg. So the sample variance sigma s square is 31.11. As the calculations are very simple, weights are tabulated, then take the difference between the individual weights and the mean value of the weight, square it and take the sum. Then the general case, standard deviation calculation, divided by the number of degrees of freedom, take the square root. That will be the standard deviation. The original value with prior to taking square root, that is the variance. Here the null hypothesis will be the sigma s square is equal to sigma p square, that is 31.11 is approximately equal to 20. Here, when we use the chi-square statistics and apply the equation, that is sigma s square by sigma p square into n-1, the value comes out to be 13.999. There are available data, critical data tables for chi-square. I will show you in the next 2-3 slides. The chi-square tables for certain degrees of freedom and the levels of significance. From that, you can easily read out at 5% significance level, the critical value or the tabulated value is around 16.92, whereas the calculated value is 13.99. If you see the table for chi-square at a different significance level, say 1%, then the value is around 21.67. At both the significance level, the chi-square value calculated is less than the critical value. That means the null hypothesis is acceptable. What does the null hypothesis say? That this variance of the sample variance, calculated variance, can be compared equivalent to that of the proposed variance, that is 20. So in conclusion, we can say in this problem, the sample can be said to have taken from a population whose variance is in the range of 20 kilograms. So just by seeing the data and the population variance, we come to the conclusion via the chi-square statistics. Chi-square statistic, as I told you, can be applied as a non-parametric test without doing much of the calculations in the evaluation. Actually, parametric and non-parametric are two different nomenclature in statistics. In parameters, we define certain parameters like mean, standard deviation, variance, relative standard deviation, like that, and compare the properties. Here, we presume that the sample population follows certain distribution. Earlier, we assumed that it follows Gaussian distribution. So there are certain presumptions and some parameters assigned to the sample population. Then we define the statistics. It becomes a parametric statistic. If no such definition or presumptions are made, it becomes a non-parametric without any predefined thoughts about the population. You are approaching the particular parameter. So chi-square is such a simple parameter. It can be used as a non-parametric test also in order to see the goodness of it between two comparable data sets or whether these data sets are independent of each other just by seeing the distribution, nature of the distribution. So that way, chi-square can be used either as parametric or a non-parametric function. When we see the goodness of which, again, the null hypothesis will be both the distribution, both the parameters, both the functions have identical distribution. We have seen different distributions such as binomial Poisson, normal distribution, Bernoulli, T distribution, rectangular, triangular, so many distributions we had discussed in the previous classes. Then from the observed data, if you compare this observed data with the available data, if they both have comparable performance, comparable frequencies of data distribution, then we say that these two, whatever data we have accumulated during our experiment and whatever is reported in the literature, they overlap very well. That means null hypothesis is acceptable. Chi-square test can easily be used for this sort of evaluation. Again, it is like a simple application of the chi-square without doing much of involved mathematical calculations also. If at all you see that they have different properties in their distribution, frequency distribution, if they are sufficiently well apart, well defined apart, then we see that they have visible divergence between each other. This could be not only due to random variation or fluctuation in some other parameters. These are representatives of two different populations. That way we come to the conclusion. If the null hypothesis is getting hold, that means both are identical. If not, they have different distribution, then alternative hypothesis becomes valid. Similarly, it is the other way around. If we propose that the null hypothesis that the data points are independent, the proposition is different here. Null hypothesis is that they are independent. Then what happens if we apply this test and the chi-square parameter comes to be less than the calculated one? Then we say that the null hypothesis is invalid. They are comparable. For example, somebody is proposing, someone is preparing a new set of medicine in certain ingredient, which is mainly controlling a particular type of fever. So if you plot the amount of or the quantity of that particular ingredient causative factor for improving the fever problems, then if you plot the amount of that particular ingredient in the medicine and the chances of getting control over fever as two distributions, two observations data sets, and compare their distributions, if they have overlap, they have similarity, they have comparable properties, then we say that they have some mutual dependence. They are associated. One property is the cure of fever is associated with the presence of this particular ingredient in the medicine. So that way, just by seeing the nature of the distribution, nature of the chi-square curve, we can come to the conclusion. These all are valid when we have large number of data points. Whenever we have smaller number of data points, say less than 5 or less than 10, these final inferences may be under question. Chi-square distribution, as I told you repeatedly, is generally used for assessing data having large number of points, large number of inputs. One such example, so for if you if you are choosing cards randomly from a huge set of cards, infinite deck of cards, around say one person is picking out around 1600 cards from that large number of cards, and he is getting around say 441 hearts, 404 spades, 402 diamonds, and 353 clubs. Then he has got around 1600 cards in total. Can we say that these suits are equal, or whether they are having unequal sets of suits in the entire data points. That means whatever the otherwise, if all the suits are identical, our observation would have been 400 hearts, 400 spades, 400 diamonds, and 400 clubs. That will be the ideal situation. But in real situations, you see that if the deck is not uniformly distributed, the cards are not uniformly distributed in the deck, you will see random presence when you are picking out different types of cards from that entire set. So initially, we proposed that the number of the probability of taking out hearts is equal to that for spades and diamond and club. But what we observe is different frequency for each of these different types of cards. From the chi-square function, we can calculate the values and it comes out to be around. When you do here, the expected frequency will be the ideal case where each set will have 400, 400, 400 of number of cards. Total is 1600. 1600 is equally divided. That is the expected frequency or the ideal frequency. Whereas you see that only 353 clubs are obtained when one is randomly picking. Whether this is due to random variations or the suits are not equal. That is what we are trying to evaluate. Here is the critical data table for the chi-square function. One part of the entire big table is only given here with a significance level of 0.05, that is 5% significance level. You can see in textbooks on statistics for different significance level and large collection of critical data tables for chi-square. Whatever is relevant only given here. Since there are four variables, four number of measurements, say hearts, spade, diamond, and clubs, 4 are the contributors. Degrees of freedom becomes 3 and significance level, if not mentioned, we go for 5%, that is alpha 0.05. So from the table, the value, critical value reads out to be 7.81, whereas the calculated value comes out to be 9.77. As the calculated value is greater than the critical value, the null hypothesis is to be rejected. Alternate hypothesis is supported. The discrepancies are too much. That means the suits are not identical. There may be intermixing of several suits. Some of the suits, some cards may be missing in those suits. Clubs may be missing mostly because those numbers are less. Similarly, this is another example for you to have hands-on experience for calculating the chi-square values. When we read the burette, one particular burette to the second decimal of the volume, the final digit can be anyone from 0 to 9. If 50 such readings are taken for the volume of a particular liquid, we see that the last digit, the least significant digit, that is a second decimal, can be 0, 1, 2, or any digit up to 9. If one person is doing 50 such readings and taking the frequency of a particular digit, occurrence of a particular digit and tabulating, the data comes out to be like this. For example, we have to see whether this is whether the person is having certain bias to a particular digit. For example, some people like even digits, so they tend to read towards the nearest even digit. Some people have some bias towards the digits like 5 or 0, like that. From this observation of frequency of reading a particular digit, can we come out with a conclusion stating whether this person has certain bias to certain of the digits or not? Here again, we can calculate the chi-square and come to the conclusion. Since there are 50 such readings and each of the digits from 0 to 9 has got equal probability of occurrence in the expected range, then we can calculate the expected frequency to be 50 divided by 10, total number of data points, that comes out to be 5. Whereas observed frequencies are given in the purple color on the top. Those are tabulated here again. The same way we calculate the difference between the observed and expected frequency, divided by, take the square and divide by the expected frequency, sum it. That way we calculate the chi-square value. And you can see the degrees of freedom comes out to be 9 because there are 10 such individual data inputs. Then the chi-square value comes out to be around 16.8 in the calculated one, whereas the critical value is 16.92. So it is marginally less than the critical value. From this data, hence we conclude that there are no preferences or choices for certain digits over the others. The data is reliable. The whatever variations in the number of frequencies of observations are due to only random variation. The person does not have any bias towards any particular digit. That is the conclusion we draw from here. In another case, for example, around 4 people are there in a laboratory, and it happens to be the case over a period of time, these workers break the glasswares, and the frequency of that glassware breakages are noted down and compiled over here. Whether we can say that all workers have the comparable reliability, or the one who has broken least number, say 9 glasswares only, is a better performer compared to the other one who has broken around 24 glasswares. Can we conclude from this data? The number of breakages are given. Whether we can pick out the person who has done only 9 breakages, who has broken only 9 glasswares, whether he is more reliable than the other one. Here again, the chi-square statistic will help us to take a conclusion. You can see that 4 people are being compared. So the number of degrees of freedom will be 4 minus 1, 3. The critical value of chi-square comes out to be 7.81, whereas the calculated chi-square is around 8.96. Here we see that the calculated chi-square is greater than the critical chi-square. That means, yes, there is evidence that the workers do differ in their reliability. We come to the conclusion they have different skill levels. We can pick between those workers. As I told you earlier also repeatedly, when the number of data points are lower or smaller, less than 5, or the frequency of observation, if the frequencies are lower, what we will do? We combine classes together. If even the data points themselves are low, then one has to be very careful while applying this chi-square function. And when the degrees of freedom comes down to 1, you have to apply a correction which is known as Yates correction. Here, O minus E, observed minus expected frequency, gets modified as O minus E minus 0.5. That is the general case. So that way, O minus E, if it were 4.5, after Yates correction, it will become 4.5 minus 0.5, that is 4. So when we are tackling a small number of data points and we are trying to apply chi-square function, chi-square statistic, be careful. Wherever required, you apply the correction factors also, because the distribution properties also get modified away from the distribution, becomes away from the normal distribution. So these are the characteristics of chi-square test. This is in general a non-parametric test. You can do compare the statistic, then mathematically also you can do. However, this does not tell us about the magnitude of the frequencies comparison. And it is used for testing of the hypothesis, and is not useful for the estimation, that we will see in the next slide again. And this test possesses additive property. For example, if we have certain degrees of freedom in a particular set of data and later on we keep adding data set to this one, you can modify the chi-square value as the degrees of freedom gets expanded as well as the cumulative chi-square also. You can just keep on adding. The additive property is valid for this statistic. And when the contingency tables become complex, more than 2 data sets on either side, then this test can be used as an initial estimator. Later on, you may have to modify appropriately so that you get to the correct conclusion. And there are no rigid assumptions in this test, easy to carry out. So people try to take up this test initially, then later on quantitative analysis, people go ahead with the other statistics also. Be careful while applying this test because it is very useful, but at the same time, when the observations are less or they have only limited frequencies, then this test sometimes will mislead you in some cases. Okay. Only when the individual observations are independent, that also is a very important factor. The observations do not interact or the parameters do not interact with each other. If at all while observing, while taking the measurements, there is an interference or effect from the other parameters, definitely one has to be very careful while applying chi-square. It is better not to take up this test. And if at all there are small theoretical frequencies, small values only, then they should be dealt with very special care also. And there are chances of committing mistakes while when we do neglect the small frequencies or nil frequencies, and sometimes the summation if we fail to do, or one has to keep in mind that O minus E factors always add up to 0. If you are not getting that, there definitely there is some mistake. You have committed some mistake. That way, you can have a self-check also. Then be careful while doing the determination of degrees of freedom and writing down the computation in their calculation also. If at all there is anything wrong in the computation, your final assumption, final conclusion also will go wrong. As I told you in the previous slide, the chi-square value, even though it gives some graphical relationship between the two data sets being compared, it does not provide any idea regarding the magnitude of their relation. We only see visually. So it cannot by itself provide an estimate of the magnitude of the association or the disagreement or the goodness of it between two such data points. What we do is we normalize it with the number of data points and convert the chi-square data into another function called the phi function. Okay, this function will have a better idea regarding the magnitude of the correlation. And even this phi function is applicable to only 2 by 2 contingency table. So you have more than 2 by 2 data points, set of data points. Another parameter, another statistics called the coefficient of contingency needs to be applied. The equation is given here. If you have more set of data points to be compared, coefficient of contingency or the mean contingency should be used. This again is a non-parametric function, can be easily applied by using this equation. As I told you, if you have to compare the variances of several such data points, one can adopt the F test, that is variance ratio test, where the magnitude of the variances are easily compared and conclusions are made thereof. It can be done for comparing more than two means or more than two means, and in linear regression analysis also it can be applied. The variance ratio is called the test is called the F test, and it is generally used for comparing the precision of the two methods and their magnitudes are being compared. So the conclusions will be more reliable when we do the F test. When you have to only graphically see and take a decision, you can go for chi-square test, but you have to mathematically see prove or disprove some association or difference between two data sets, go for F-test. And here again, the assumptions are there, the populations follow normal distribution. Or normal distributions are followed by those data sets which have more than 30 number of data points as the inputs. When we do the F-test, what we do, we take the square of the standard deviation, that is the variance, and take the ratios. And general suggestion is that take the standard deviation value which is numerically larger on the numerator. So if you go to any F table, statistical table in the literature, you will see that the F values are always greater than 1. The compiled F values are always greater than 1. Here again, the degrees of freedom have hold. The numerator degrees of freedom are represented. Numerator, say if it has got n1 number of data points, the degrees of freedom will be n1 minus 1. Denominator, if say it has got n2 data points, the degrees of freedom will be n2 minus 1. So the F table, how to read it, that we will see just now. The critical values of the F also depends on the significance level also. If not mentioned, as I told you for the T table, here again we go for 95% confidence level. In some tables, you will see the significance level, that is nothing but 100 minus confidence level. If the null hypothesis is true, that is a very ideal case, then you will see that the variance ratio is almost 1, very, very close to 1. Whereas in real situations, you will see that the F values have got numerical values greater than 1. However, if the calculated F value comes out to be less than the critical F value, then the null hypothesis, as we had repeatedly seen, the null hypothesis holds on. There is no significant difference between their variances. Variances of the two sets of data, 1 and 2, are comparable. In the case of T and Z, we had seen the two-tailed as well as one-tailed test. F-test also can be applied for the two different sets. For example, one variance is expected to be larger only all the time. Then you can do this upper-tailed t-test. If at all one variance is supposed to be lower, then you go for lower-tailed t-test. If both are comparable, you can propose the null hypothesis. Null hypothesis as both variances are comparable. The more the deviation of the F value from the unity, the stronger is the evidence of unequal variances in the two populations being compared. These are the inferences taken from one-tailed as well as two-tailed F-test. The critical values of F from one of the literatures are shown here. Normally, when we have different degrees of freedom for numerator and denominator, the general observation is that degrees of freedom of the numerator is done in the different columns from left to right. Degrees of freedom for the denominators are arranged in different rows. First, you go for the degrees of freedom for the numerator, then come down in the rows for reading the particular value. We are comparing the variances S1 square and S2 square. 1 stands for numerator, 2 stands for denominator. And the significance level also will be mentioned. If not significance, confidence level. This is a particular case where 95% confidence levels are reported for F values. One worked out example is here for you. As a part of an inter-laboratory study, one river water sample was sent to 2 laboratories. Each lab has done 8 repeated measurements. Then the individual values are given. We have to see whether the reported values, whether these two values have any significant difference in their precision or the lab between the two labs. If at all one lab's precision is better than the other, we can take up that lab as a better performer in future comparisons. That is the idea of doing this exercise. As I told you, there were 8 repeated measurements and individual values are given compiled here. you can see, you can calculate the standard deviation and variance also. Calculate those standard deviation and variance. From this table, we can read what is the critical value of F for 7 degrees of freedom for the numerator, another 7 degrees of freedom for the denominator, then come to the critical value of F. This way we do. We go from left to right for the numerator, top to bottom for the denominator. This point will be the cell corresponding to the critical value of F. And the standard deviations of individual measurements are given. You can calculate the mean, standard deviation and variance. The standard deviation ratio, variance ratios comes out to be around 2.07. All of you may give a try to do this calculation, very simple. Maybe you can take help of your calculator or Excel computer. At 7 degrees of freedom for each numerator and denominator, the critical value is around 3.787 as we read from the F table. Since the calculated F value, that is 2.07, is less than 3.787 critical value, there is no significant difference between the precision of the two laboratories. Both are comparable performance. We cannot differentiate which lab is a better performer. Both are, as far as this test is concerned, both are equal performer. This exercise is to see whether one person is proposing a new method for the determination of one parameter, chemical oxygen demand of water. And he has data from the standard, via a standard method already reported in the literature, and the standard deviation for that standard method also. And the proposed method also is showing the same value. Same mean values are same for both the standard as well as the proposed method. Then which method is superior as far as the precision is concerned? How can we take a decision? Just by seeing the standard deviation, you see that 1.51 is better, but whether we can come to the conclusion or not, mathematically one has to numerically prove it and take the decision. Here again, the F test is the tool of choice for us to do this particular test. And here, since one has to establish the supremacy of one method over the other, you normally go ahead with the F single-sided, one-sided F test. One is having better precision. And as I told you, the poorer standard deviation or the larger numerical value is taken on the denominator, smaller one in the denominator, so that you get values more than one always during the calculation. Here again, the number of determinations were 8 each. So the same value comes out. You will have 3.787 as the critical value, and the calculated F value is around 4.8. As the calculated value is more than the critical value, the null hypothesis is rejected. Null hypothesis is that both are having comparable precision. As is obvious, the new method has got lower numerical value of variance, standard deviation. It is having better precision than the already existing method, standard method, at 5% probability or 95% confidence level. So that means the new method has got an edge over the standard method. It is superior to the previous one. So further later on, whenever one requires to do the determination of chemical oxygen demand of similar samples, one can adopt this proposed new method. Here we end for the day. If anybody has any doubt, you may please write in the chat box. If anybody has any doubt, you may please write in the chat box. Otherwise, during the checking, I will summarize. We had seen the t-test, how to read the t-table, then the number of replicate measurements, the judicious choice of number of replicate measurements, and the reliability interval, chi-square test, chi-square test in various practices like goodness of fit comparison between the experimental and observed data, the interdependency or independence of two or more data sets, then the phi coefficient and the correlation coefficient we had seen. Then finally, we had gone ahead with the F test. The next class we will have like brushing up of the F test, and further we go ahead with the other statistical tests. If there are no doubts, we wind up for the day. No. No doubts are seen in the chat box. See you in the next class.